In this video, we are looking at one of the most common and damaging mistakes you can make in a FastAPI application, placing a blocking call inside an async function. It is easy to do by accident, the error is silent, and the performance impact can be severe. Let us break down exactly what goes wrong and how to fix it. When you write async-def in FastAPI, you're making a promise to the event loop. Whenever this function has to wait for something, a network call, a database query, it will pause and let other requests run. But if you call a synchronous blocking function instead of an async one, that promise is broken. The thread is occupied, the loop is stuck, and every other user's request just waits in silence. Think of the event loop as a single cashier running a checkout line. The async model works because the cashier can delegate waiting tasks, a price check, a card approval, and keep serving other customers in the meantime. A blocking call removes that delegation. The cashier disappears into the stockroom, and absolutely nobody in the queue gets served until they come back. There are 3 legitimate escape hatches. First, swap the blocking library for an async-native one and await its calls. That is the cleanest path. Second, if the work is synchronous and you cannot change the library, define a plain def route instead of async-def. FastAPI automatically runs plain def routes in a thread pool, keeping the event loop free. Third, if you need async context but must call a sync function, use async-io's run_in_executor to push it off the loop thread. Look at the first route, bad sleep. It is declared async-def but calls time.sleep, a plain synchronous call that never yields. While it sleeps, the event loop is completely frozen. The second route, good sleep, replaces that with await asyncio.sleep. The await keyword hands control back to the loop so other requests can proceed. The third route, sync work, is a plain def, no async keyword at all. FastAPI detects this and runs it inside a thread pool automatically, so the loop stays free. The fourth route demonstrates the manual thread pool approach. Run_in_executor offloads the synchronous_blocking IO function to a thread, then awaits the result, keeping the event loop responsive throughout. FastAPI sits on top of Starlet, which runs inside Uvicon's asyncio event loop, a single thread that handles all concurrent requests by switching between them at every await point. When you write async-def and use await, the event loop can juggle hundreds of requests with minimal overhead. But a blocking call has no await. It simply runs to completion on that one thread, and nothing else can proceed until it is done. FastAPI's automatic thread pool for plain def routes is the framework's own defense against this exact problem. The rule is straightforward. Use async-def when every IO call inside that function has an async-native counterpart you can await. If you are working with the synchronous library, an old database driver, a third-party SDK, any call to time.sleep. Either switch to a plain def route and let FastAPI handle the thread pool for you, or explicitly use run_in_executor. Never try to hide synchronous work inside async-def and hope for the best. To summarize, the async event loop is powerful but fragile. One blocking call breaks the concurrency for everyone. The fix is always one of 3 things. Use an async library and await it, drop to a plain def and let FastAPI's thread pool handle it, or manually push the work off the loop with run_in_executor. Pick the right tool for the type of IO you actually have, and your API stays fast under load.